Hello, this is Shomo from UT Austin. Motivated by the problem of demographic-specific toxicity detection, we introduce a new conditional multitask learning framework. One challenge we encounter with building a toxicity classifier for content moderation is that toxic language has commonalities and differences across the various groups for which it targets. So when building a model, we would like to learn these general patterns of linguistic toxicity while distinguishing the differences as well. But a one-size-fits-all approach risks overfitting forms of toxic language most relevant to the majority groups, potentially at the expense of systematically weaker model performance on minority groups. This also raises concerns of algorithmic fairness. So we pose the question, can multitask learning help us in this situation? We propose modeling demographic targeted toxic language via MTL. MTL combines shared and task-specific layers, which allows the model to specialize on relationships relevant to different groups while leveraging shared properties across groups. In our toxicity detection setting, any post targeting group A should influence the weights of shared and task A layers only. Task B and C layers should remain unaffected. With respect to who's being targeted from the set of all possible posts, we have the following scenario. Posts can either be toxic or non-toxic, targeting neither, only one or both groups as color-coded. In traditional MTL, each training point needs to be labeled for all the tasks. However, this is not the case in our toxicity detection setting, as this would mean that a post targeting group A only is assumed as non-toxic for group B. This schema risks label contamination across groups. To illustrate label contamination, a post targeting group A only is implicitly marked as non-toxic for group B, even when the post is not targeting group B at all. This could mislead the task B branch, as it would learn to associate linguistic toxicity with a non-toxic label. Our conditional MTL approach is capable of learning group-specific representations of toxic language over sparse labels. We introduce a task-specific conditional representation of labels and avoid labeling instances which do not belong to a particular group, toxic or otherwise. This updated labeling schema combined with a novel conditional loss function allows for model training without label contamination. In our updated labeling schema, a post that is not targeted at group B is marked as irrelevant for group B, toxic or otherwise. Thus, only group-relevant labels affect the task-specific losses. With our updated labels in place, where each example is a collection of posts and group label, we forward propagate all the examples in the current batch through the network to both the branches. In the backpropagation phase for each branch, only the group relevant examples are chosen and the cross entropy losses are calculated on the subset of relevant examples, which thereby updates the weight of the task-specific layer. In the backpropagation phase, both the task-specific losses additively influence updating the weights of the shared layer, which thereby is updated by all the examples, learning their shared characteristics. To evaluate the performance of CondMTL, we consider different baseline models. The first one we consider is the stacked STL variant, which learns individual classifiers over each group. All posts represent the union of group A and group B. For experimentation, we use the Distilbert feature weights, and they were kept frozen during model training. Any other representation can be chosen without altering the architecture or the loss schema. Our second baseline is the widely used cross-stitch MTL variant from the computer vision community. It consists of cross-stitch units between the stacked STL layers that allows the task-specific layers to communicate amongst each other. The third baseline is the traditional MTL model with shared and task-specific layers, where all the layers are affected by every post. While our conditional model is similar to traditional MTL architecture-wise, with every post influencing the shared layer, the key difference between these two architectures is that the task-specific layers in CondMTL are influenced by posts only relevant to the task, getting rid of the label contamination issue. We use the civil comments portion of the WILDS dataset, which roughly has a 54 and 69% of posts targeting men and women, with some posts common across groups. Overall, and within each group, toxic language is rare, comprising around 15% of posts. Thereby, any classifier trivially predicting every post as non-toxic would achieve 85% overall accuracy. Thus, we need to look at other performance metrics for meaningful evaluation. While we study toxic language directed at men and women, in this example, we acknowledge that gender is a non-binary construct in reality. Looking at overall weighted F1 scores, CondMTL has the highest value. Although overall numbers are high, there exist nuances when we delve into class-specific numbers. When we break down the toxic to non-toxic examples, we see the performance over toxic posts is degraded across models due to label imbalance, something which is not evident from the overall numbers. Failing to detect toxic posts can cause more harm than misclassifying non-toxic posts. Hence, we focus on group-specific recall values over toxic posts. Keeping the F1 score over toxic posts now, let's observe the precision and recall values, where recall signifies the capture rate of toxic posts by the classifier. Specifically for recall, we see a poor performance across all models. This is compelling evidence empirically that hate speech is far from a solved problem, and that papers reporting much higher numbers may be missing important, harder aspects of the toxic language detection problem. Stacked STL serves as our primary baseline, being the decoupled classifier for comparison against MTL variants. Cross-stitch MTL, which architecturally built on stacked STL, allows tasks to communicate, has increased precision. However, the recall rates drop significantly. Traditional MTL has poor recall performance due to label contamination. Considering all the models, stacked STL and CondMTL have significant improvements in the toxic cases, where CondMTL has better recall values. This is because CondMTL does not suffer from label contamination, while being able to learn both the general patterns and difference in linguistic toxicity. In addition to having better metric values compared to stacked STL, CondMTL has the added benefit of having significant parameter reduction and massive improvement in model training time. To summarize, toxic language has commonalities and differences across the different groups for which it targets. Conditional MTL allows us to model the commonalities while tailoring predictions for differences, giving us the best of both worlds. For more information, please refer to our GitHub link. Thank you.